It's 12:30, and as always, I have so many things to cover, so I'm going to go ahead and get started. So just a couple of reminders that I'll be at my office this evening and also tomorrow. And also I have my normal office hours as well. So I can just do as much as tutoring as possible and answer your questions. You have your SI Pass leaders that they write their hours every session, right? And I encourage you to go there and seek help. Also, you have tutoring at second floor of the library, so we have so many resources for this class. And you have your homework due tonight, and also your quiz 4 due this Friday. And I posted them way in advance, so I expect you to do them. And as I mentioned, I don't guarantee that I have makeup for your next exam and this quiz, because we're just getting close to the end of the semester. I'm barely catching up with writing makeups for all of you, so just try to do your best and take it for sure, okay? And yeah, I think that's that. And also the makeup exam 2, as I mentioned, makeup exam 2, we're going to have them this Friday, 3 to 6 p.m. And I'm going to send an announcement about the location. I tried to reserve this room, but it might be occupied till 4. So I'll just check where is available, so we don't have to worry about that. And I told you, if you cannot make it at that time and you want to make up exam 2, just email me and we will work out something. And also for quiz 3, if you wanted to make that up or make up for that, just email me and I open it for you. Okay, and some of you already did and I opened that for you. Any questions about any of this? Okay. And I have some students emailing me that they're putting an effort, but they're not getting a good grade. So we have, and I emphasize on this during my classes, that there is a difference between just reading and learning. Some of you, you're taking notes, you're reading, but you're not exactly comprehending what is happening, right? So make sure when you read each sentence, you know what that means. And sometimes I ask the students, what is an element? And I see students just read from the board, but they're not understanding what they're saying. So in order for you to succeed, you should read and learn, okay? And if you have any questions or difficulties, come to me, talk with me. And when you want to succeed, I make sure that happens. And we can talk to your classmates, students from last semester, as long as you care. I provide you with extra credit opportunities. I do several things to make sure that you succeed, okay? But you should put the effort. And feel free to just ask me any questions that you have. And I try to show you all that I'm understanding. I take your suggestions seriously, and I try my best to accommodate all of you. Any questions? Okay. So last session, we talked about the fact that when we give an element energy or heat is one sort of energy as well, right? So if we give heat or energy to an element, what happens is that the electron in that element will be excited. So for instance, if it's I was looking at you and then the pen was going down. So if the electron is here, for instance, in n equal 1, and we're talking about, this is Bohr model, right? Remember that we had different orbits. The other thing that is really important with this chapter, you have lots of things to study and memorize. And what I did, and if you looked at the previous slides that I posted on Canvas, I copied and pasted the pages of your book. So even if you don't have the book, you have the material to study, and I'm going to ask you from those. So there is no excuse that you couldn't study those. I just copied and pasted. Hopefully I don't go to jail for copyright infringement, but you have the course materials, and I did the same thing in this lecture. I have your book basically in the slides, so you can go back, study, and all that, okay? So in Bohr model, we had orbits. Okay, n equal 1, n equal 2, n equal 3, and this n theoretically can go till infinity. Okay, but this is what we're dealing mostly, n equal 1, 2, 3, and I talk about the other shells or orbits later on. So if, for instance, in hydrogen, we have one electron, this electron is here. If we give hydrogen atom energy, what happens is that this electron will be excited and travels to a higher energy orbit. And it's important for you to know that n equal 1 has the lowest energy among these orbits. So if I tell you which one of the following has the highest energy, n equal 1, n equal 2, n equal 3, n equal 4, which one has the highest energy? Exactly. Highest energy, n equal 1 has the lowest energy. Okay. So when you give energy to an electron that was in n equal 1, you will excite that electron. So it goes to a higher energy level orbit. And depending on how much energy you give to that electron, maybe it just goes to n equal 2, right? Maybe it goes to n equal 3 or n equal 4, depending on how much energy you give that single electron. But it's important to know that the electron won't land somewhere in between, okay? So you cannot have an electron that is here. It would always be in one of the orbits in Bohr model, okay? And this electron that now is in n equal 3, in this example, for instance, and I'm going to cross out this one, so it shows you that this electron cannot be in between. Remember the Bohr energy ladder? We cannot stand between the two steps of the ladder, right? I encourage you to try to do that. That won't happen, right? So this is the same here. Your electron won't be in between these energy levels. That's why we say the energy of each orbit is quantized. There is certain amount of energy that these electrons, or this electron in this case, can have. And when electron is excited, it has more energy. And now it's unstable. It wants to go back to a lower energy state. So what happens is that when the electron is coming back from the, for instance, now your book showed another electron, so it would be easier to demonstrate because I already messed up here with writing so many things here. So if you have an electron that now travels to a higher energy state and goes back to a lower energy state orbit, it releases the energy as light. That is why we have neon lights. So we give electric energy to neon atoms, and when the electrons are going back to lower energy states, they emit the energy as light. Any questions? So when you go back and read the book that as I said, I included in these slides, and for this subject, it would be the previous lectures, I included the slides. If you don't understand any sentence, just reach out to me so I can explain that to you. And here, again, is like the summary of what we learned before. When we're talking about Bohr model, we have different orbits. And I'm going to introduce another terminology this session in quantum mechanical model, and I'm going to ask that in your exam as true or false. So this is really important that you know that in Bohr model, we just talk about orbits, okay? Or we can also call them shells. There are like different shells or different orbits around nucleus. Okay. And the other thing to remember is that if we had white light and we would pass it through a prism, we would have a continuous spectrum. But when we have like different elements, we see just single, kind of like distinct lines. And each of these would be different colors because they will have like different amount of energy. And I just randomly colored this. But you get the idea, okay? So if you see distinct lines, right, and they're not continuous, you have an element. You don't have white light or visible light. But if you see a continuous spectrum, that would be white light. And this is the subject of your lab this week. Some of you already saw that how you can identify different elements if you know the spectrum of different elements, right? Any questions so far? This is kind of like review of what we already learned. Does that make sense? Okay. And we talked about Bohr diagram, and I told you to remember that when you have the nucleus and you have like these orbits or shell around the nucleus, I try my best to have a good circle. There are maximum number of electrons that can be in each shell. So you should know that in n equal 1, we have maximum 2 electrons. In n equal, so this was n equal 1. In n equal 2, we have maximum 8 electrons. 3, 4, 5, 6, 7, 8. And it doesn't matter where you put these electrons, as long as you know n equal 2 has maximum 8 electrons. And n equal 3 has maximum 18 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I pair them up, so it would be, okay, this one was a little, disorganized. These are 2. 2, 2, 2. So it would be 18 in total. So if I ask you, write the Bohr diagram for fluorine, for instance, how would you do that? Fluorine. First, you look at the periodic table, see what is the atomic number, right? We said that when the atom is neutral, the number of protons and electrons are the same, right? So fluorine, the atomic number is 9. We have 9 protons. It means that we have 9 electrons, right? So here you have your nucleus, which has like 9 protons, and it has like roughly 9 electrons. But again, this was one question that one of your friends asked me the other time, which is a great question. Like, why this number here has decimal point, right? This is the atomic mass. Can anyone tell me why it has decimal point? Yes?
Because it's an average of the most common isotopes of that order.
Exactly, because fluorine has different isotopes, so the number of protons is the same, but the number of neutrons differ. And depending on their abundance, we took an average and reported this number, right? So you can roughly say, for instance, fluorine doesn't have 20 neutrons, right? Or like 100 neutrons. But you can exactly say based on this number, because we have like different isotopes. And the way that I asked that in your exam before, I gave you, for instance, F18, and I told you how many electrons, protons, and neutrons it has. If I give you like that, you know that this 18 is number of protons plus number of neutrons, right? That is the mass number. And you know the atomic number of fluorine is 9, so it's basically solving this equation. 9 plus number of neutrons is 8. What would be this number? 9, right? But if I just give you the average mass or atomic mass and I say what is the number of neutrons, you ask me which isotope you're talking about, okay? So that's what's kind of review that you're going to see on your exam if you're taking makeup exam 2 on Friday, and you saw that previously on your exam 2. But now we're talking about electrons, okay, in chapter 9. So we have 9 electrons, and I told you, remember that we have different shells, okay? So now n equal 1, n equal 2. How many electrons should I put in n equal 1? 2. That is the maximum, right? I cannot put more. So how many electrons in total I have in fluorine? 9. I already put 2 of them on the first shell. How many are remaining? 7. So I put 1, 2, 3, 4, 5, 6, 7. And again, it doesn't matter how you put them, as long as you know 7 are in N equal to. And the number of electrons, I'm going to write that. Number of electrons in the outermost shell or orbit is called valence electrons. Okay, that is terminology. So when you have Bohr diagram, the outermost shell in this case is N equal 2, right? You count the number of electrons in outermost shell, and that gives you the number of valence electrons. So number of valence electrons, now I'm going to kind of scroll up. So number of valence electrons in fluorine is 7. Can anyone tell me what group in the periodic table fluorine is?
The halogen.
Exactly. What is the group number? It's 7A. Okay? So remember that. Let's do another example. If I tell you, write the Bohr or draw the Bohr diagram for oxygen, how would you do that? Oxygen has a nucleus, right? So this part is kind of like universal for all. And hopefully you do a better job than me drawing the circles. So this is N equal 1, this is N equal 2. So you can just do that for any question that you see, you know. We don't necessarily have to fill N equal 2, depending on how many electrons we have. But in the case of oxygen, what is the atomic number? 6, right? 8. 8, always check. So it's 8. So how many electrons are in N equal 2? How many can I put? 2. I told you the maximum is 2, you should remember. So I already put 2, I have total of 8. How many is remaining? 6. So you put 1, 2, 3, 4, 5, 6. Okay? So number of valence electrons in oxygen is 6. Can anyone tell me what group in the periodic table oxygen is looking at? 6A. Do you see a trend? So any group, main group element that you're dealing with, for instance, carbon, can anyone tell me, based on what we did right now or the trend that we found, how many valence electrons carbon has? 4. Exactly, because it's in group 4A. So now I promise you that things that we learned is gonna come together and makes more sense. So this is how the periodic table is arranged. So in each family, each group of main group elements, they have similar properties because the number of valence electrons in their group is the same. Okay, any questions? Any questions? Yes?
So do all stable elements have to have 8 valence electrons?
What do you mean the stable elements? Do you mean that they don't have charge?
Like noble gases, for example,
Uh-huh.
reactive. Is that because they have 8 valence electrons in their shell?
Exactly, because they have 8 electrons in their valence shell. All of them except helium that has just 2, right? Because their valence shell is filled, they don't want to lose or gain electrons. They also don't want to share electrons. And we're going to talk more about that in chapter 10 when we're talking about like different types of bonding and see what happens then. But yes, exactly, because now they have 8 electrons in their valence shell, they don't want to lose or gain electron. But here, for instance, for oxygen, you see that if oxygen gains 2 electrons, right, it reaches the electron configuration of neon. That's why oxygen, I told you previously, just remember O will be O2 minus. It gains 2 electrons. I didn't tell you why. I told you you can remember 6 minus 8 minus 2. And I tried kind of to explain this, but at that point we didn't have the necessary tools to learn this. But now this is the reason that oxygen gains 2 electrons, but fluorine gains 1 electron. Or your halogens in general, they gain 1 electron. Does that make sense? Any question about this? Okay. The other thing that we talked about during the last class is that if we excite an electron and it goes to a higher energy shell or orbit, you see that I kind of interchangeably use these words. You know, shell is the same as orbit. Is these circles in a sense? I mean, in paper would be circle, you know, right? In space would be kind of like this spherical shell around the nucleus, right? But when they go from n equal, you know, in this example, your book didn't say that originally where the electron was. It said, imagine that this is excited, this electron, and all of them gained some energy and went to higher energy level. Now, when they lose energy and come back to the lower energy level, they lose energy as we said, light. And depending on this energy difference, right, higher this energy difference, the light that is emitted would be having higher energy. And as we said, higher energy corresponds to higher frequency. Higher frequency corresponds to shorter wavelength, okay? And that is one thing that I'm going to ask you in exam. Which of the following lights emitted by an excited electron after going to the lower energy state would have lower wavelength? And you can, based on this diagram, see which one has higher energy, and based on that, answer the question. Does that make sense? Any questions? Okay. Now I have like a summary slide that I took from your book, which is, I included these, and also I included your textbook because I'm going to ask you in exam, okay, true or false, or, you know, which of the following statement is correct, incorrect. And I had students last semester were telling me, or telling their TA, that they don't like true or false, or like, you know, memorization questions. And also they said they don't like solving mathematical problems. And I'm like, so what should I ask you? I'm like telling stories, you know, or like, there should be a way for me to see, you know, if you learned or not. That's why I have like a balance, a combination between theoretical and also mathematical. Even if you're not good at math, you can still study and get a good grade, right? And that's why I devoted points to SI pass tutoring with myself, because even if you don't do well on homework, if you just do 2 sessions of tutoring each week, you can easily make up for that, right? So I'm trying to do my best to be fair. And as I said, I always accept suggestions too. But I feel like having theoretical questions help, right? I can also give you 25 mathematical questions. Who wants that? Anyone? So you see, that's why I'm trying to kind of like balance it out. Anyway, so electrons, and this is, you know, how you should study. I'm kind of like studying with you. Electrons exist in quantized orbits. So you should ask yourself, what did quantized orbits meant, right? So what it meant is that if I have nucleus here and I have n equal 1 and n equal 2 around it, right? Each of these orbits, they have certain amount of energy, right? And energy of n equal 1 is less than energy of n equal 2, right? And that continues. And also, if you have an electron here on n equal 1, it has certain amount of energy associated with it. And we said that, you know, these quantized orbits that are at a specific fixed energy and a specific fixed distances from the nucleus. Okay? So in my drawings, every time I draw it differently, but theoretically, this n equal 1, the distance from nucleus is certain amount, and the energy associated with that is quantized. Does that make sense? When energy is put into an atom, electrons are excited to higher energy orbits. So we know now what excitation means when we give heat or energy to an atom, and the electron would go to higher energy level orbit. For instance, if previously it was in n equal 1, now it goes to n equal 2. Remember that this amount of energy and this amount of energy in n equal 2 is different. So depending on how much energy we give to this electron, we excite it to higher energy level orbit. And remember, this electron won't be in between two energy levels. Okay? Okay, next one, I changed the color. When an electron is in an atom relaxes or falls from a higher energy orbit to a lower energy orbit, the atom emits light. Okay, remember, now if this one wants to go back to n equal 1, it emits light. And depending on the energy difference between n equal 2 and n equal 1, depending on that energy level, the wavelength would be different. And depending on that wavelength, we see different colors. If, depending on what the energy level is. Does that make sense? Okay, the next one says the energy and therefore the wavelength of the emitted line corresponds to the energy difference between the two orbits in the transition. Since these energies are fixed and discrete, the energy and therefore the wavelength of the emitted light is fixed and discrete. Okay, so any questions about that? So if you comprehend what you're reading, when I just change the terminology, you should still be able to answer the questions, okay? So if I say electrons do not exist in quantized orbits, for instance, right? You should comprehend the sentence so that when I change it, you also comprehend, because sometimes you see the sentence, it seems familiar, so you just say true, but I'm going to change it for the exam. Any questions? Good? Okay. So you may wonder, I briefly mentioned quantum mechanical model, and when I was teaching this, I told you Bohr model is entirely correct. It's not. So that's why there are another model to correct the deficiencies associated with Bohr model. But now we want to know what was the deficiency. So when we had the spectrum of light for hydrogen, Bohr model beautifully describes that. It predicts where are the lines, what are the wavelengths, and all that. But when we have more electrons, so hydrogen, as you know, it only has one electron, okay? But when we have more than one electron, Bohr model couldn't explain the emission spectrum of the elements. It was wonderful for hydrogen, but it wasn't that good for the other elements. Can anyone tell me why do you think that is? So I told you, in the case of hydrogen, we have this positive nucleus, and we have only one electron in n equal 1. So if we give energy to this electron, right, it can go to n equal 2, and depending on how much energy we give to this hydrogen, maybe this electron again travels to n equal 3, right? So it can be different combinations, and I'm just writing this as an example, so I don't want you to memorize where it goes. It's just an example, okay? But what I want you to know is that depending on where this electron goes back, right, And for instance, if I have another orbit here, for instance, n equals 4, so now I see 4 different energy differences, right? So basically, in the emission spectra, I see 4 different lines, right, for hydrogen. And as I said, I just draw this as an example. It doesn't correspond to emission spectrum of hydrogen. But just as a rule of thumb, you see 4 lines, right? And they have different energy levels. So you see like 1, 2, 3, 4 different lines. Kind of like gives you an idea of what is happening, okay? So now I'm telling you that if I have 2 electrons, now scientists could not predict the emission spectrum of helium, okay? Before I just continue teaching, can anyone guess why that is? In case of hydrogen, we only have 1 electron, 1 proton, so there is only interaction between 1 electron and 1 proton. So that is straightforward. But when we have more electrons, you have the interaction between each of these electrons with the nucleus. You have also the interaction between electrons, right? So if you have 2 electrons, there is some sort of, repulsion between 2 negative electrons. Does that make sense? And I don't want you to know the specifics, but I just want you to know why Bohr model failed to predict the emission spectra of all the other elements. It was only good for hydrogen. Because now when we have more electrons, we would be having interactions between these electrons as well. And also each of these electrons with the nucleus, they have like different interactions. And also the protons in the nucleus, they have like the repulsion between them. And if we add these terms together, we would be having Schrödinger equation. And you might have heard of that in quantum mechanics, which we're not going to cover in this class. But basically, what I want you to know is that Bohr model could not predict the emission spectrum of any other element rather than hydrogen. Okay? And that's why scientists came up with the quantum mechanical model. Okay? And before I just cover this part of the text, your book basically just wrote what I told you. Okay? So, and as I said, I included this because I'm going to ask you in your homework problems and quizzes and exam. So the great success of the Bohr model of the atom was that it predicted the lines of the hydrogen emission spectrum. So what I do in exam, I substitute hydrogen with helium, or like neon or argon, and the sentence would be false, right? So each sentence that you study, ask yourself, how can I change that, right? Or why it makes sense. However, it failed to predict the emission spectra of other elements that contained more than 1 hydrogen. For this and other reasons, the Bohr model was replaced with a more sophisticated model called quantum mechanical or wave mechanical model. Any questions about this? Good? Okay. And here your book still wants to emphasize that, okay, Bohr models is still important, because sometimes when one model is incorrect, we don't do much with it anymore, kind of like, Thomson model, right? Plum pudding model. Now we don't visit it anymore, so it was like, it was more incorrect than Bohr model. I guess you can put it that way. But Bohr model is still really important and helps us to solve so many different questions. So that's why we're still using it, but we know at the back of our minds that electrons are not exactly arranged how Bohr told us, okay? So the Bohr model is still important because it provides a logical foundation of the quantum mechanical model and reveals the historical development of scientific understanding. So still we use Bohr model even in quantum mechanical model, so that's why I really emphasize on that model. Any questions? Okay. So now we have, like always, some terminology to remember before I can continue with the lecture. So first of all, it's really important to know, and I always ask this in exam, and always the students get this wrong. So in Bohr model, we talk about orbits or shells around nucleus. In quantum mechanical models, we don't work with orbits anymore. We have another concept named orbital. And I'm going to just momentarily in the next bullet point tell you what orbital is. But again, as I said several times, I have this slide here to emphasize this is important, and I'm going to ask you that. In the quantum mechanical model, Bohr orbits are replaced with quantum mechanical orbitals. So anytime you hear the word orbit, we're talking about Bohr model. When we're talking about quantum mechanical model, we have orbitals. Okay? So in Bohr model, we had orbits around nucleus, and we said exactly if I have hydrogen atom, we have one electron, and this electron is exactly in n equal 1. It said this electron, and if this is like n equal 2, it told us this electron is not here, is not here, is not here, is not here. It's in the n equal 1 orbit. Okay? So what quantum mechanical model tells us is that it's not as that easy. When we are talking with electrons and how they are located around the nucleus, we're not talking about exact location. We cannot say the electron is exactly in n equal 1. No. We can estimate or say probably where the electron is. So what we do is that if we have like this nucleus here, right, and we have like the electron, we can say that probably it's here, maybe it's here, maybe it's here, and then we record kind of at each moment the probability of where this electron can be. So we have a probability map, okay, and I have the pictures in the next slide, and I know that when I record the lectures for people who watch, a few people that watch the lectures at home, if I turn the lecture, if I turn this slide, it kind of like breaks my talking too, and based on this slide, so I try not to go back and forth between the slides, but I have the picture of this in the next slide. That's what I'm saying, is that it's kind of like if you consider, in real life, if I tell you, where, for instance, if you say where Lida is at like 2 p.m., right, on campus, on, let's say, on Wednesdays, right? So you cannot exactly tell, unless I just tell you that I'm sitting at my desk, I'm at my office, you cannot tell the exact location. Maybe I'll be at this class, maybe I'll be at cafeteria, maybe I can be at different locations, right? But still, you can have an idea based on the pattern that you see, right? If there is a camera attached to me, and then when I go different places, like during the course of a semester, probably probably at 2 p.m. is, right after our class, probably I'll be, let's say, at University Co-op eating lunch, right? I'm just making up an example. So it's not exact, but you can say probably where I'll be, right? So this is the same concept with the location of electrons. Does that make sense? So just paraphrasing what I said, orbitals are different from orbits in that they represent probability maps that show a statistical distribution of where the electron is likely to be found. Is that clear what this sentence means? So it's a probability map of finding an electron in certain location. Orbitals do not represent the specific paths that electrons follow. Okay, so unlike here that we said for sure electron is in this orbit, when we're talking with orbitals, when we're talking about orbitals or dealing with orbitals, we don't exactly know where the electron is, but we have a probability map that I have the picture in the next slide. Any questions so far? Good? Okay, so before showing you the picture, I have more terminology, and as I said, anytime that I'm teaching something, I have also the section of the book in case you're reading the book. So we have some terminology. One is principal quantum number, and principal quantum number is the same as orbit in Bohr model. Okay, and also it's the same as your shell. And we denote that by n. We call that principal quantum number. And even in Bohr model, I call them n equal 1, n equal 2, n equal 3, and so on. So the definition is a number that indicates the shell that an electron occupies. Okay? Any question about that? And as I told you, we're going to use Bohr model in quantum mechanical model too. So it's really important for you to know that well. Principal shell. So principal shell is the shell indicated by the principal quantum number. Okay? Any question about that? So here we call this n equal 1. So this is 1 is the principal quantum number, and then this shell, we call that n equal 1 principal shell. So the shell, we call it, the orbit, we call it shell, but the number is the principal quantum number. Okay? Subshell, and again, we're adding definitions because now we're dealing with quantum mechanical model. So we have a shell number or principal quantum number or orbit, and we have subshell. In quantum mechanics, subshell specifies the shape of the orbital and is represented by different letters S, P, D, F. And I'm going in the next slide talk more about this. So what you need to know, as well as all these things that I wrote, is that in Bohr model, we have only n equal 1, n equal 2, n equal 3. We have orbits. In quantum mechanical model, we have orbitals, and we denote orbitals with a number and a letter. So 1s, this 1 tells me that n equals 1. This s tells me that what is the shape of my orbital. This tells me the principal quantum number. This tells me what is the shape of the orbital. Okay? As I said, I'm throwing lots of definitions at you, and that's why you should study them. So I'll be having like easier time to teach these things. The other definition is ground state. The ground state is the lowest energy possible for an electron to be. Okay? So the state of an atom or molecule in which the electrons occupy the lowest energy orbitals available. So we call that ground state. Okay? And the other thing, and I'm going to highlight with orange, is excited state. And we already talked about that. So this shouldn't be that complicated. And then a stable state for an atom or molecule in which energy has been absorbed but not re-emitted, raising an electron from the ground state into a higher energy orbital. Okay? So here we talk about orbitals instead of orbits, but the concept is the same. Basically, we had an electron in lower energy orbital, we give it heat or energy, and it goes to higher energy level orbital. Any questions? Good? Okay, so now, as I promised, I have the shape of different orbitals. So I told you, when we want to denote orbitals, we have like a number and a letter. So the number tells me what is my n. S tells me the shape of the orbital, and I'm going to show you how. So as I told you, we have, when we're talking about orbitals, this is the probability where electron can be. So scientists, physicists, and chemists, they did the work, and they just now we're using what they already did, the results. So they mapped the probability of where electron can be, for instance, when we're dealing with like hydrogen atom, which is only having like one electron, right? So if you have only one electron, and that can be for like higher energy states too, and I'm going to talk more about that, later. But imagine that we have one electron, and that is the lowest, that would be having the lowest amount of energy possible, right? So that electron at one point it can be here, and as I said, they recorded the location of this electron at different times. So at one time it was here, 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 and when they put all these locations of the electron together, they saw a sphere-like shape. They saw that this specific orbital is a spherical. Okay? And that's why the s orbitals are spherical. Okay? And this is kind of like representation of like the shape. Here you see also the electrons, and here you see like kind of both of them. Both the electrons and the shape. But this is how we get basically when I tell you one s orbital is a spherical, this is what I mean, is that if we record the location of electrons at different times, it would be a spherical. And that is why in orbitals we have probability map. Because if I ask you, is the electron here for sure? You say, no, it can be here, it can be here, it can be here. So we put all the possibilities together and we say s orbitals are spherical. Okay, and I asked you to read the next slides, basically your book, to understand things better. If you don't study this chapter, you're not going to learn. As simple as that. Now, if I do the same thing for p orbitals, and as I told you, we have like one letter, one number. We can have 1p and 2p, or like 3p, right, and so on and so forth. So we have also p orbitals. So if we do the same for p orbitals, and I'm not going to repeat every one of them, all of them, but we see that the shape for p orbitals is dumbbell-like. You see that we have like kind of like this infinity shape. It's kind of like dumbbell. If you go to gym, most of the equipment, most of the weights are like dumbbell-like, right? Anyway, so that is the shape of p orbitals. And as I said, scientists previously did that, and now we're just using the results. And I'm not going to ask you the shape of d and f orbitals, but I asked you what is the shape of s orbitals, and you tell me spherical, or p would be dumbbell-like, okay? And more than that, I won't ask you. And it is important to know that whatever the number of shell is, you have to that amount number of subshells. So if you are in n equal 1, we have 1 subshell. If you have n equal 2, we have 2 subshells, and so on. So as you see, I included your book basically here, so make sure to read that. And I have your attendance along with 5 questions that I asked you. And for each question that you answer correctly, I'm going to ask 2 extra credits to you. So do your best to answer the questions. And as I mentioned several times, if you don't study this chapter, most probably you're not going to learn. And if you answer the question after the class, I'm not going to accept that. So just do your best right now. And I have students emailing me, like at 2, that I cannot make, I couldn't make the link work. If you have any issues, just come to me right after the class. I don't accept attendance after the class. And for the people that just, at the end of the class come by the door and do the attendance, overall you want to learn. So, I don't know.